Okay, great. So we have our next speaker, Sebastian, who's going to tell us about new insights on neutrino interactions and dark matter from CMB data.
Thanks a lot. Thank you very much for having me. It's great to be here, really. So I'm going to talk about dark matter interactions with neutrino. Before I start my talk, I would like you to take a look at this bottle. So this is a pretty ordinary bottle. I'm not going to do any magic with it, so no worries. So I'm just going to treat it as a container of relic neutrinos. So knowing how many of them we have more or less around us and what's the size of this bottle, we would expect that there is about 100,000 of relic neutrinos inside. But how do I really know, right? So even if I trap all of them inside, which is not possible, but let's say I do some magic, and even if I make it entirely out of lead, then it's still going to take orders of magnitude longer time than the age of the universe for at least one of these neutrinos to interact inside. Still, I'm going to try to do some crazy thing and tell you that these relic neutrinos can actually have a strong impact on what we observe, but I'm going to make this bottle very special. So it's going to be, first of all, made out of dark matter, and second, it's going to be much larger, of the order of the size of the universe around the recombination and before that. So first of all, my talk is based on these papers with Phil Braggs from Paris and Karsten van den Broek, Eleonora Di Valentino, and William Guerre from Sheffield. So before I go into any cosmological data, just let me give you a very brief motivation. Why do we even consider dark matter interactions with neutrinos? So, as you might know, probably the best motivated candidate for dark matter, I can put it there already, is the so-called weakly interacting massive particle, or WIMPs, right? So there is a very powerful paradigm behind WIMPs, which is the thermal production. So the early universe, we say, was a thermal plasma that contained dark matter particles, and then it expanded, cooled down, and the comoving number density of these particles basically has frozen out. We call the process freezing, as you can see, and then this sets the relic density of dark matter nowadays. And this gives you also a very clear target to search for dark matter interactions, and there has been many searches for this over decades. And then you can also say that maybe dark matter is like ordinary matter, and in the case of the ordinary matter, what we believe about is that there was a lot of matter and antimatter in the early universe, and then basically all of them was wiped out by efficient annihilations, and then only a slight overabundance remained of matter. The same could take place in the dark matter sector if we believe they are both connected to each other. And this is called the asymmetric dark matter. So both the thermal paradigm and the asymmetric dark matter have this nice feature that they predict that dark matter should interact with at least some of the standard model species relatively strongly. So then you can search for these interactions. The only problem is that we don't see this, right? So no matter how nice story it is, it's just not there. It's too harsh statement, of course, because we keep searching for these. There are avenues in which you can find this stuff and so on. But one thing that we need to keep in mind is that among all the standard model species, neutrinos, if they serve as a bridge to the dark matter, this is the possibility that has been much less tested than the others. So there's much more room for this nice picture to stay if dark matter connects to the standard model via neutrinos. And there is more to this. Besides the fact that neutrinos can be the last man standing in this game, on top of this, we know that neutrinos do oscillate. So basically, flavor eigenstates and mass eigenstates are not the same. They change. There has been a lot of experimental evidence for this. You see various neutrino sources and so on here. And importantly, a consequence of this that many people believe might be the case, although it's still hypothetical, is that there might exist sterile neutrino. So additional neutrinos that we add to the standard model, right-handed neutrinos, that do not interact electroweakly and not strongly. So they are even more difficult to probe than normal neutrinos. So what I will be interested in is this scenario in which dark matter talks to standard model via neutrinos, but specifically via the sterile neutrino that then talks to neutrinos. In this case, dark matter interactions with all the other species of the standard model is highly suppressed, so you avoid the bounds. You are fine with them. And still the question is, how do you probe this dark matter? You can have this thermal dark matter picture, the asymmetric dark matter. This is all nice, but how do we probe this? And it turns out that cosmology is a very promising window This is a picture of the energy density as a redshift. So you go to the early universe prior to the recombination. You see the densities grow, including neutrinos, which is these blue curves here. So we go to the dense and hot universe, and that's the place in which the neutrinos and dark matter could interact very efficiently. All right, so that was intro about the dark matter neutrino interactions. And then, yes.
So you say that in your model, the sterile neutrino is not the real dark matter, it's extra sterile neutrino that talks to some other dark matter that you just keep
yes.
Okay, that's very important because sterile neutrino itself is a good candidate for long dark matter, as you know, and I wanted to make sure that my brain was.
Yes, no. That's a very good point, precisely. So what I'm going to be interested in is a cold dark matter, so something like a standard lambda CDM picture that talks to standard model via sterile neutrino, which is not dark matter itself. Yeah. All right, cool. So how do we search for them? I will be specifically interested in looking for this in the CMB data. So there has been many analyses of this over the last, let's say, 2 decades that I list some of the papers here. So one thing that we need to remember, of course, neutrinos do have impact on CMB. I think I don't need to explain any of this to this audience here. They can have this drag of the baryon photon fluid effect that is measurable. We can try to learn something about neutrino masses on this and so on. But then what happens if we, on top of this, add efficient dark matter neutrino interactions? So first, let's focus on very strong interactions between dark matter and neutrinos. So if this is the case, then these interactions can be as strong that even at some stage neutrinos cease to be free streaming. Basically, they form a dark matter neutrino fluid, like the baryon photon fluid, which has a different velocity. And as you can imagine, this has a very strong impact on various CMB peaks. So this is the results of, that have been summarized more recently in this paper of the work of these many people. And you see the baseline CMB spectrum, which is somewhat black in this picture, and then various colors correspond to different strengths of the dark matter neutrino interactions. I'm going to use this parameter U throughout the talk, which basically has the cross-section of dark matter neutrino interactions, tell me how often they interact, which is normalized to the Thomson scattering cross-section, and there is some dark matter mass normalization. So you can see basically a visible effect barely by eye. But we do like our CMB spectrum, so we don't want to be distorted that much. So what we learned from this basically is that there are bounds on dark matter neutrino interactions from the CMB data that have been studied. So the focus of my talk will be on this picture, but in the high multiple regime, especially here, that has been overlooked in the past. So what we did with Eleonora, William, and others, we basically studied this first at the general level, without even adding additional data to this, by extending the picture to, as you see, up to a few thousand the multiple range. So what we are interested in this talk is that dark matter neutrino interactions that are significantly lower than the ones that have been studied in the past. In this case, you don't really expect much impact on the low multiple spectrum that is probed by Planck. You can see it here, to some extent, and better here. So this is the difference between the normal one and the one modified by dark matter neutrino interactions. The lower we go here, the lower is the coupling strength of dark matter neutrino interactions. So you see the effect can be at the level of 10 to minus 4 or even lower, so basically not measurable. On the other hand, as you go higher and higher with multiples, the effect becomes stronger up to the level of few percent and basically maybe even 10% or so. This is the regime, we call it, actually not we, but the other people call it mixed damping regime, in which there's a lot of neutrinos around and also some amount of dark matter. So if the dark matter neutrino interactions is relatively low, then in this mixed damping regime, what we see is that neutrinos can easily interact and impact dark matter, so can drag it and basically wash out the small structures. On the other hand, there is too few impact of dark matter on neutrinos, so neutrinos do free stream normally, and you don't see much impact on the low multiples here. So what we found in these papers, that's the first lesson of my talk, and is that this high multiple CMB data is basically a new window to constrain dark matter neutrino interactions and to probe this asymmetric dark matter regime potentially the thermal target of dark matter. Then the other thing that has been done in our paper was to take actual data, and you see all sort of data sets that we did, temperature and polarization from Planck, lensing, ACT data. It was later also updated by William and Eleonora and others to act the ACT data release 6 and SPT, South Pole Telescope data, basically similar conclusions. So we sample over the lambda CDM parameters. We add additional one, which is the strength of the interaction between dark matter and neutrinos in our picture. And what we what we find thanks to this is that by combining both the Planck and ACT data, we can basically, in this picture, with a low dark matter neutrino interactions, we can reconcile the standard Planck picture that is all fine and basically not affected, but we still improve the fit in these high multiple peaks that are basically driven by ACT. So this can be quantified even more in terms of a preference towards non-zero dark matter interaction that we see in the data, and we've done this. So by studying this preference, you can find the best fit value of this U parameter. This basically tells you the best fit value of the dark matter neutrino interaction that we predict, which is much lower than was previously considered. You see the value here, basically, it's some parameter, but strikingly, we have found that it's very similar to the previous analysis of the Lyman-α data that was also considered dark matter neutrino interactions and improved fit to this. And you see both these values are very similar to each other. And you can see the table of standard model, standard cosmological model parameters here. If we just have ACT alone, that we spoil many parameters, but if we have ACT plus Planck plus BAO, then basically most of the parameters go back to their original values, and we have additional degree of freedom with the dark matter neutrino interactions, and we find this preference. I want to now just present you a specific model. I'm not going to talk about the details of this dark matter neutrino interaction model, but I was telling about precisely this bridge, which is the bridge between the dark matter sector and the neutrino sector that goes through sterile neutrinos. So we did study this first at the general CMB level and the plots that I've shown you and the data fit, and then we try to apply it to a specific dark matter neutrino interaction model that you see here. So this is the dark matter neutrino scattering that goes via the sterile neutrino, which is this capital N, and there is additional scalar particle that you just need to introduce for the completeness of the model. So important feature about this is a pretty simple thing, but you can reconcile this asymmetric dark matter picture in it, and you can make the neutrino dark matter interaction that depends on the temperature. You can see it here. This is the U parameter, but it's maximized around the time prior to recombination. So this is this black curve, and depending on some other value model parameters, it can also have this peak at different positions. But for some values at least, it's maximized prior to recombination, and then it drops down at later times. So the CMB is precisely the best time, the universe prior to recombination, to constrain this model and to test it, basically. And needless to say that in this scenario, this dark matter interactions with all the other standard model species is highly suppressed, so you avoid other bounds. So we did this, we analyzed this, and this is the very busy plot. I'm not going to explain everything on it, but just very briefly. So this is the result for the dark matter mass. You see it's an MeV range, so mega electronovolts, 10 to 100, and this is the interaction strength of dark matter with the neutrinos, basically. So all the gray shaded regions are excluded already. So even though it's much more difficult to probe this model than the other ones, there are still bounds on this. They basically come mostly from the search for the sterile neutrino, because we keep searching for sterile neutrinos as well. So this is this thing, and the Big Bang nucleosynthesis excludes this one. Importantly, this black dotted region here is the thermal target. So this is the place in which you can have correct Rayleigh density via the thermal production mechanism that I advertised for WIMPs. And then above this, the white region here is the asymmetric dark matter region, in which you basically have the same story as with normal ordinary baryonic matter. So So these are the bounds. There's a lot of other lines here, but the most important ones for my talk is these blue lines here. So these are our results, including also this purple region here, which is the bound. And between these two blue lines, that's the region that has best fit to the CMB data according to our analysis. And then the sort of reddish shaded region here is the Lyman-α best fit, had a better statistical significance. It's a lower one, but you see they both overlap quite well. And it's going to be also probed by DESI and also, hopefully, by the future CMB data. So that with this, I think I'm going to conclude now. So what I wanted to say is that thermal dark matter and asymmetric dark matter is a very attractive framework. I'm a particle physicist, so I'm telling from the perspective of particle physics. But importantly, it has been under siege experimentally. But there is a window for dark matter to interact with neutrinos, and this window still remains to be explored. Cosmology, and specifically CMB data, is the place at which we can actually do this. So what we have shown in our papers is that the small-scale CMB measurements with few % accuracy open a new window to study dark matter-neutrino interactions. And then there is also a preference for the non-zero coupling that we found. It's not 5 sigma at this stage, it's a preference. Similar hints were earlier found in Lyman-α data. So the future hopefully will bring more stuff into this. Thank you very much.
Questions, comments? Yeah.
Hi. So, what kind of dark? So, is your dark matter your dark matter is fermion, right?
Yes, my dark matter is fermion. Actually,
so your dark matter interacts with sterile neutron as scalar, right?
No. This sterile neutrino is also fermion. This n is fermion, but this thing is scalar. This is additional particle. However, I could make the other one dark matter. It's just a choice, and actually, the other choice could also have nice features. But you have two BSM species and the additional one which is sterile neutrino, so 3 in total in this scenario. And then I decided to make the fermion as a dark matter. I could make this one as a dark matter if I'd made it like.
But in this scenario, how do you stabilize your dark matter? Is it stable?
Yeah, so it's I didn't show any Lagrangians, but you can basically involve some Z2 symmetry and so on. If you make this guy to be the lightest of all the BSM species, then it remains stable.
Yeah, because this can interact with standard model Higgs and lepton, right?
You mean the?
I mean, if you do not have a Z2 symmetry, it can interact with standard model Higgs and leptons.
Which one? Sorry.
Chi.
5.
Yeah. Chi.
Yeah. No. We just assume this interaction, and then let me show you the Lagrangian maybe. So what we assume is that this chi interacts only with these new sterile states, and the sterile state mixes with the active neutrino interactions, and that's the way the interactions with the standard model neutrinos enter the game.
Yeah, so you need to assume certain symmetry, right? Without assuming symmetry, you cannot do it.
Yeah, I mean that's the but you don't have a. I think you said that you do have couplings to charge leptons. You do not have it in this picture because they do not arise in this only at the higher level.
No, what I'm saying is that if you do not assign a symmetry to chi.
Yes, of course, yes.
It can interact with standard model Higgs.
Yeah. That's what we do. Yeah. That's. Mm-hmm. And you make it the lightest of all these guys, because otherwise it also decay into the dark states here.
Okay, thank you.
I have a question about where you get these sterile neutrinos and how much of it you need to get the interactions going. So is it coming out of the total neutrino budget?
No.
Or is it like an extra thing?
No, it's a. Oh, sorry. It's just an extra thing. We don't count it in the total neutrino budget because we assume, for our purpose, it's like 100 MeV particle or so, which decays. It only appears in this Feynman diagram. So it basically, the thing is that if you introduce sterile neutrino to the game, then the thing that you call normal neutrino has a bit of a mixture of a sterile state. And thanks to this, it does interact with this dark matter thanks to the fact that it has a bit of a mixture of the sterile state. So that's the only level at which sterile neutrino appears in the scenario. But we don't count for it in the energy budget or the delta N effective or whatever.
Okay.
Stuff
But
like
do
this.
you have to assume a certain amount of it to get any effect?
Well, yes. I mean, it's not an amount of particles, but you need to assume a certain amount of a mixing between active neutrino and the sterile one. And the point is that there is still a large room for this mixing, especially in the tau neutrino sector. So that these are the bounds that I've shown. Sorry, here, these grayish bounds here. So the point is that we don't care about how many of them were produced in the early universe and then decayed. We only care how much the normal neutrino, how large is the admixture of the sterile state in it. So how much BSM physics is hidden inside it. And this is driven by this coupling constant G here. It does have a coupling constant from the interaction to the regression and also the mixing angle hidden. I didn't want to discuss the details, but you see the mixing angle here. This is called the U parameter. So there needs to be a certain amount of this mixing. So there is also a way to probe these models by searching for the sterile neutrino itself. And these are the gray shaded bounds, and the future Bell2 is an accelerator-based search in Japan that will also carve partially this, but there is still this region that is much more difficult, and we hope that CMB could actually test it.
Thank you.
I hope, yeah.
Any other comments, questions? So if not, we thank the speaker.